Welcome everyone, and this is our webinar, and let me think, this is our probably third or fourth one. What do you think, Laura? Or maybe
fourth.
2, 3, 4. Yeah, fourth webinar, and we really want to thank you guys for your support, and I think the webinar series has been a very good success, and just get a whole range of talks, and this is really wonderful. Before I introduce our first speaker today, I would like to advertise for our next webinar, which will take place 2 weeks from now on the 26th of August, same time. So very easy to remember. And we'll be sending out reminders and links for you to, a link for you to register for the next webinar. Now we'll shift our center of gravity to Western Australia. So we'll have 2 speakers from WA. Debbie Sylvester Dean will be one of the speakers, and I think Debbie is here with us today. And then we'll also have Amir Carton from, Debbie is from Curtin University, and Amir from UWA will also be giving a talk. So we really look forward to our webinar in 2 weeks. So please remember to join us. All right, so let me introduce our first speaker today, Dr. Cameron Shearer. And Cameron's here with the camera on, so all good, and slideshow is there here as well. Okay, so Cameron is a native of Adelaide, and he received his PhD in 2012 in the group of Joe Shapter. And then after that, he went to Germany, to the University of Munster to do a postdoc. And then returning to South Australia in 2014, first as a researcher at Flinders University, and then an ARC postdoc. And then in 2018, he became a Beacon Research Fellow at the University of Adelaide. And just last year, he received a very prestigious ARC Future Fellowship. And then for the next few years, he'll be focusing his attention on research. So I think that's enough introduction for Cameron. And I think now you can tell us your cool research. Take it away, Cameron.
Okay. All right. Thanks a lot for the introduction, Tack. And everyone, I've tried to keep the top right-hand corner of the screen free of important figures and things. If you wanted to move the video to the top right-hand, it might look the best that way. But I can't guarantee that at some point something's going to be overlooked. So this is the work I completed at Uni Adelaide with Greg Mather, and we received some photocatalytic material from a group in Japan, in the group of Kazunari Domin. So everything today is going to be about hydrogen. So basically, hydrogen can react with oxygen, forming water and releasing a pretty good amount of energy. And this hydrogen can be used to replace petrol in vehicles, such as this hydrogen-powered car, which is it's an electric vehicle which uses a fuel cell to run. Or also it can replace natural gas, basically wherever natural gas is used, such as in homes. In fact, most of the pipeline in Australia is already suitable to be for use with hydrogen. But what would need to change is the fixtures in the different burners. So hydrogen, when it's used, it produces only water and energy. So if hydrogen is made from just using water and sunlight, it would be a completely renewable and non-polluting fuel source. And so if we're using sunlight, then hydrogen is very light, there is the option for Australia to export its solar energy worldwide. So instead of exporting coal and oil energy, we could be exporting a green energy source. So there are many different ways in which we can create hydrogen from water, and one of them, the one that I'm going to talk about today, is photocatalysis. And then the reaction I'm looking at is water splitting with photocatalysis. So TAC asked me to put in a pretty decent introduction for photocatalysis. So I'm going to go through this in, I think, good detail, but I do have the chat open if I miss anything or something isn't quite easy to understand. So basically, photocatalysis is a light-assisted catalysis where we use the fact that some semiconducting materials can absorb light. So we have a semiconductor with a filled valence band and an empty conduction band. When it's, and these are typically just powders of different sizes. But when these semiconductors are illuminated with light with energy greater than its band gap, it can become excited, producing a excited electron and leaving behind a hole behind it. So one thing to avoid in this case is the recombination, where it just relaxes back to the ground state without doing any positive reaction. Well, what we want to see is we want to use this electron and use this hole to complete chemical reactions. So the hole, for example, can drive oxidation reactions, such as the oxidation of water into oxygen and hydrogen protons. Meanwhile, the photo-excited electrons can drive reduction reactions, such as the reduction of protons into hydrogen. So you see that both of these processes are multiple electrons transfer processes. And so the surface chemistry and other things need to be set up to drive these reactions to completion, so they don't just go back the other way. So the method used to do this is to employ co-catalysts. So typically we're looking at co-catalysts here being metallic nanoparticles for the reduction reactions, such as rhodium or platinum, which are pretty small in size. And in the case of the hydrogen evolution reaction, the platinum, first of all, acts as an electron sink to kind of remove the electron away from the hole to prevent recombination. It also then allows the multiple step process for hydrogen evolution reaction to occur. And then in the case of the oxidation reactions, we can also have a co-catalyst specific for these, which are typically metal oxides as well, such as cobalt oxide. So this is a T image of a typical photocatalyst with the large semiconductor nanoparticle coated in a large amount of smaller co-catalyst nanoparticles. So the last part of the reaction is we want to see the products released from the surface. And something to be avoided is the back reaction. So the catalysts, which are typically very active for the hydrogen evolution reaction, are also very active for the back reaction of water production from hydrogen and oxygen. And of course, this reaction is an exothermic reaction. And so basically, this has to be avoided to really improve the efficiency of the process. So the way to do this is actually to add an overlayer coating onto the hydrogen evolution reaction catalyst. And this coating is made to, first of all, allow protons to diffuse through to create hydrogen, but restrict oxygen from actually being able to interact with the surface of the hydrogen evolution co-catalyst. So So here's an example here that we got from another group in Japan, where they have coated chromium oxide onto a gold nanoparticle. So in this case, the gold nanoparticle would be the hydrogen evolution catalyst, and it's coated by a thin and seemingly porous layer of chromium oxide. And in this case, the protons can move through the chromium oxide, but the oxygen cannot. And so that really drives the reaction forwards and stops the back reaction from occurring. Okay, so at the moment, what's the best photocatalytic material, and why is it the best photocatalytic material? So it's, and this is the photocatalytic material that I'm going to be using later on in my reactions, where it's aluminium doped strontium titanate with rhodium chromium oxide and cobalt oxide. So there's a lot of steps going on, but each of these materials has its own role. So the aluminium doped strontium titanate is the light absorbing semiconductor. The rhodium is the hydrogen evolution catalyst, which exists as small nanoparticles. The chromium oxide is this overlayer to prevent the back reaction from occurring. And the cobalt oxide is our oxygen evolution co-catalyst. So I'm not going to go into it too much, but basically this cobalt actually assists in stopping the chromium oxide from being consumed by the oxygen as well. So it has a few roles. So here's the TEM image of what it looks like, and then we can take with the electron microscope, we can also take elemental maps of the surface. So here we have a different color for the different elements involved, and the rhodium in purple we're seeing is coated by the chromium oxide in green. So I have take a line scan through this line that's just come up, and it highlights how the rhodium is present on the surface of the strontium in this case, and then the chromium has this just small enough overlayer to prevent that back reaction from occurring. So a question that I kind of ask everyone is, how do you know you're good at your job? And so I ask everyone, because I'm always concerned that I'm not good at my job, and I'm trying to work out how can I tell someone that I am. And photocatalysts kind of think the same way. So when looking at photocatalytic data, how do you know that it's good? So I have my list of key figures of merit that I look for. So the first is that the hydrogen production with time is linear. So basically it's a straight line here, which means that the production rate isn't changing with time. If it was changing with time, it would mean that there is degradation of the photocatalyst system occurring. The second thing to look for is that the ratio of hydrogen and oxygen is 2. So the stoichiometry of the reaction tells us that for every 2 hydrogens, there should be 1 oxygen. So the next is to look for a high apparent quantum yield, so QY. So this is basically how efficient electrons are absorbed and then turned into hydrogen molecules. So a higher number is better. So and this is at a specific wavelength as well. So we normally look at the wavelength where the semiconductor absorbs the most light. So the next thing is the solar to hydrogen efficiency. So it's one thing to have a good apparent quantum yield at like a very UV or a UV wavelength, but ultimately we want to be using sunlight to create hydrogen, and this is where the solar to hydrogen efficiency comes in, where when you use solar light to illuminate the photocatalyst, what potential power from the hydrogen do you get compared to the power of the solar spectrum that's put in? So this is basically the same number as and efficiency of a solar cell. And then the final value is how much does it cost, or how many dollars does it cost per kilogram of hydrogen? So how simple is the system, how expensive are the products, and how much can it be upscaled? All come into what this dollars per kilogram could be. So we're not yet at this level, so I don't have dollars per kilogram values. In fact, I'm mostly going to be looking at steps 1, 2, and 3 of my figures of merit. But I mean, ultimately, when you make a photocatalyst to create hydrogen, you want to see that you're making hydrogen. And so this photocatalytic materials have really improved a lot. So I first started working in my postdoc in Germany in 2012. And at that stage, no one was seeing this type of reactivity from a photocatalyst. This is the material that I'm going to be using later on. So we have pure water. This is being illuminated by a light source. This one might be a solar simulator, I can't remember. And we're seeing hydrogen and oxygen bubbles coming off from the photocatalyst, which is our white plate down the bottom here. Basically the state of the art is that we're seeing about a 2% solar to hydrogen efficiency. These particular material was recording an apparent quantum yield of 60% at 360 nanometers. So 60% of the photons illuminated on the surface are being used to create hydrogen. And in fact, more recently, the same group have increased this number up to 90%. The photocatalyst that we're going through later on is going to be this 60% photocatalyst. And something interesting that our collaborators in Japan found was that as they increased the temperature, going from right to left on this axis, they observed a higher hydrogen evolution rate and a higher solar to hydrogen efficiency. So in Greg's lab at Uni Adelaide, we have a gas phase photocatalytic reactor, which is capable of doing experiments up to 200 degrees Celsius. So we thought if the efficiency is increasing with temperature, it's perfect to do it in the gas phase where we can go above 100 degrees. In the liquid phase reactions, I think they were stopping at 60 degrees. I think was the highest temperature they had. So here's the reactor. I don't have a better photo of the whole thing, but basically this is about a 1 centimeter diameter sapphire window where the sample sits within. It's about 3 milliliters in total inside the reactor. And we have a complete stainless steel manifold system where we have the ability to okay, sorry, I just started reading the chat. I'll answer that question soon, Jeffrey. Okay, so we have our ability to create, basically evacuate to high vacuum. I'll go through one by one. I've got a picture. So we can load our sample into the reactor. We can evacuate it to high vacuum. We set the temperature for the reactor with a heater thermocouple underneath. We add water vapor from a water bulb next to it, and then I then fill the reaction mixture up to 1 bar, 1 atmosphere with nitrogen. We can then illuminate from the top with a UV LED light source, and then the gas products are monitored with a residual gas analyzer. So it's a mass spec, where I'm obtaining a mass spectrum of the gas in the mixture about once every minute. We have a pulsed valve, which allows a very small volume of the reaction mixture to go through to our residual gas analyzer at all times. This is all controlled by a PID control, which is maintaining a constant pressure at the residual gas analyzer. At the end of the experiment, the whole gas mixture is sent to gas chromatography to back up what we see in the residual gas analyzer. So I see that Jeffrey's written a question about wondering if we can separate hydrogen and oxygen so they come off separately. And yes, there are a range of different architectures that these reactions can be completed in. And some of them do have a separation between where hydrogen and oxygen come from. But these systems have an extra level of complexity, and these are not ultimately in techno-economic assessments. The more simple system where hydrogen and oxygen are produced together looks like it's going to be cheaper in the end. But that's not to say that it does really require then something to separate the hydrogen and oxygen together before the hydrogen is being used. So that's definitely a step that's required that I'm hoping someone else can do a very good job at. And there are already commercial examples. Okay, so basically I'm at this point where we've got water vapor, we've got our photocatalyst, and we're illuminating it with light. So here is the reaction of what we see in this case, where I've deliberately added water vapor and where we've deliberately added water vapor and nitrogen. So first of all, we have it in the dark. I see nothing being produced, which is a good sign. We turn the UV light on and we're seeing hydrogen and oxygen produced. So this is from the residual gas analyzer. So I do notice, so looking for this linearity, yes, it looks very linear, but what about in this first hour here? What does that look like? So just zooming in on that first hour, I do see what looks like two slopes. But it's still, well, if I fit a linear and I get an R-squared value, it's 0.99. So I'm giving myself a tick in the linear hydrogen production rate, in the linear hydrogen production rate box. And then with the residual gas analyzer, we're looking at a mass of 2, or an M1Z of 2 and an M1Z of 32 for those two. So just to make sure that we're not getting a signal from something else, the gas chromatography at the end of the reaction confirms hydrogen and oxygen present with pretty similar values for the moles in the end, which then equate to a production rate and an apparent quantum yield, AQY. And these two things do match up pretty close together. So the H2, so my figures are mirrored again. H2 and O2 ratio is a little bit above 2, pretty good. Once again, I'll give myself a tick. But what I'm not seeing is a very high apparent quantum yield. I'm seeing after this initial high rate, I see a very relatively linear for the rest of the experiment, but our apparent quantum yield is less than 1%. And we compare that to the 60% that was being seen in liquid water. And then the cost, I'm basically going to be leaving that as a question mark the entire time. And I'm seeing a question from Matthew about the quality of the water. So yes, it does make a huge difference. And the when we're looking at these oxidation and reduction reactions occurring at the surface, some other things can also be oxidized and reduced. So if the water is full of some carbonaceous material, for example, that would be oxidized in preference to water. And so we'd see different products being formed. And also different things in water can lead to the dissolution of the catalysts. So things like chlorine need to be avoided if possible. And it is one of the advantages that we're saying of our gas phase reactor, where the water would be of higher purity than other things. Okay. Now, let's look closely at what could possibly be the cause for these two slopes that I'm seeing, and then also try to explain why I'm seeing a lower AQY. So what I think is occurring is during the dark reaction, we're seeing water chemisorb from the gas phase onto the surface phase to some equilibrium value. When the UV light is first turned on, we see a high initial rate of reaction as a lot of this chemisorbed water is used in the creation of hydrogen. And eventually we find that we're at a different equilibrium state where the amount of chemisorbed water is lower than in the dark, and its rate of chemisorption onto the catalytic surface becomes the rate limiting step. Okay, and so we've got much less reactant than in the case of the liquid water system. But anyway, our point was my goal was to look at the different temperature. And so here I do a reaction where I have the temperature profile on the top axis, amount produced on the bottom axis, and I get a rate at 30 degrees, a rate then at 45, a rate at 60, a rate at 70, a rate at 90, and then I go back to 30 degrees again. And I actually see, instead of an increase of rate, which I expected, I see a decrease of rate. In fact, it starts to going negative at 90 degrees Celsius, which is a bit odd. It looks pretty flat when you look at it, but anyway. So just plotting the rate then versus temperature, we see this exponential type decay profile. And basically, if I convert this temperature along instead to the relative humidity on the x-axis and I plot the data, I see a linear fit. As the relative humidity in the system decreases with increasing temperature, we get a lower reaction rate. So I think this is, again, going back to the water adsorption of the surface being the rate limiting step. At higher temperatures, there's much less water adsorbed to the surface, and so I'm seeing a lower reaction rate. Okay, so this is where I thought, well, what else can I do with the gas phase reactor? And I noticed that, I know it's not a high production rate, but I'm still seeing something at pretty low relative humidities. In fact, Adelaide's pretty dry, but we're still looking at about 30% relative humidity on most days, 50% on good days. So why don't I just do the reaction using air? So I've got my reactions, what I did on the right here now. So basically I loaded the sample to the reactor, I closed the lid and started measuring in the dark. And then at one point I turn the light on. So normally this wouldn't even be thought of to be done because the large amount of oxygen in air will force the backward reaction to occur. So I went on and on about the backward reaction before and haven't mentioned it again, but now it's important that I would expect to see almost nothing in the case where there's lots of oxygen in the system. But instead, here's the profile that we see. So nothing during the dark. Turn the light on, we see linear at first, and then it does decay a little bit with time. And again, we see this two-step profile at the beginning, similar to what we saw in the system where I deliberately added water to nitrogen myself. I'm giving myself a yellow tick instead of a green tick for a linear hydrogen production rate. It's still quite linear for the first hour, which is okay, but it does seem like we might be seeing either some degradation of the photocatalyst itself, probably the rhodium nanoparticles, or the chromium oxide overlayer of the rhodium nanoparticles. I actually can't test the hydrogen to oxygen ratio because oxygen is way higher than the hydrogen. I can't determine if oxygen is being made or not. And then this potential cost per kilogram, I imagine, well, it would be lower than in the case where I have to find pure water myself. Just taking the reaction mixture directly from the air would be a very simple system, but of course it's going to be needing a very good separation afterwards to collect the hydrogen. That rate after 1 hour in air actually fits exactly on my trend before. So at least for the first hour, I see no difference in reaction rate between air and the water and nitrogen mixture that I make in the lab. But I do see a difference in stability. So I have relative rate on the y-axis and time on the x-axis. My crosses in the synthetic mixture, and then my triangles in the air. So I am seeing a much faster degradation of the photocatalyst in the air environment. And so, so we're thinking that the oxygen is degrading this chromium oxide overlayer, but we'll need to investigate a little bit more to be sure. And I think what we need to do really next is to develop a more robust catalyst protection system that's suitable to be used up in air. So I've shown our successful water splitting using this sodium titanate, aluminium, rhodium, chromium oxide, cobalt oxide photocatalyst. We're seeing a lower AQY than what we were seeing in liquid phase reactions. We saw a decrease in production rate with increasing temperature. And in both of these things, it's showing that the water absorption appears to be the rate limiting step, which is basically, so our follow-up reactions are going to be looking at doing these reactions in a higher water pressure. But finally, I did show that we could do these reactions in air. So we could be getting a useful fuel from a free reactant source. And so lots of people to acknowledge, but my time is up. So thank you everyone for listening. And I did skip a few questions in there too. So thanks.
I'll clap on everyone's behalf and take over. Sorry.
Thanks, Cameron. Thank you very much for the nice presentation. Right, let's spend a few minutes going through some questions here. So Jeff asked earlier on, do you get NOx if you burn H2 in air? Do you know?
I don't see it. So we get MO, the RGA looks at all masses from 1 to 67. And basically we are not seeing anything.
Oh, right.
This is our reaction.
This is when you burn it, though. I mean, do you?
Oh yeah, perhaps that was back when talking about using it in a vehicle.
Yeah.
I'm not sure.
Probably, I suppose you still would, right? I mean, that's caused by high temperature.
I think they normally actually make sure it's pure hydrogen, pure oxygen in the fuel cell.
Right. Now, so purity, that question has been addressed, and I think Meredith has had a comment that your AQY, apparent quantum yield, already takes into account concentration, so that looks like a huge loss of efficiency. So
the AQY takes into account the concentration of the light, but not into account the concentration of the water.
Okay, so I was just going to say, in the gas phase compared to liquid water,
Yep.
So you are making it up to an atmosphere with nitrogen. So
Yes.
your concentration of water is tiny to begin with.
Yep. Yes, it is.
So if you were to correct for that, it wouldn't look quite so bad.
Yeah, so that would be something nice to do, and maybe we could one day do some kind of water chemisorption experiment to compare or to determine really what our surface coverage is. But we haven't yet worked out a reliable way to do that.
Thanks.
Fair enough.
Thanks. There's also a question from Josh. Does the gas phase reactor potentially overcome the problem CO2 solubility in water when using water splitting to drive CO2RR?
So that'd be the CO2 reduction reaction, and possibly it's not something that I've really investigated myself, but I do know that one of the main intentions for the reactor when it was constructed was for CO2 reduction. So it would be a very good, it is a very good reactor for that reaction.
Great. Peter Krause has a question here. Should make UHV instruments out of this stuff if you can bake the water using UV light for in 2 hours? Comment.
So that would, yeah, that would be, you still need to be able to illuminate it somehow, but yeah.
UV light, yeah. Jimbo Chan has a question here. Is there an optimal facet of the catalytic surfaces?
So yes, there is. And this is the paper where they found, or they achieved the 90% AQI recently. They actually found an ideal facet for hydrogen evolution and an ideal facet for oxygen evolution. So the binding, I don't know that the number.
But I guess, does it get affected as a result of?
Yes. So yeah. So we haven't really looked at the catalyst after reaction, which is something that we should. I would say it's on the list, but it's been on the list for a long time. So hopefully it gets to the top of the list soon, and I'll know for sure.
That's related to poisoning of the catalyst, isn't it?
Like poisoning of the catalyst, so they're inactive, or just if they, well, yeah, come off somehow as well, and then they wouldn't be active anymore.
Right. Yeah, Elmer's Krause has a question here. How about catalysts that work at longer wavelengths? That's an interesting one.
Yes, so many people are looking at using ones, particularly which work in visible light. Ultimately, the goal is to obtain the highest possible solar to hydrogen efficiency. At the moment, the best solar to hydrogen efficiency is actually occurring with UV light active catalysts. So even though there's not much UV light in the solar spectrum, these catalysts have a much, much higher AQI at UV light. And so in the end, it's still more beneficial to use these UV active catalysts. But I think ultimately, we're wasting a lot of energy because we don't need the 3.2 electron volts to split water. We only need 1.5 electron volts. So
is there a plan to move to liquid water? Here's a question by Evan Robertson, and then he also made the comment, although quality of LA water is bad.
Well, once again, gas phase, it doesn't matter. I think that, so liquid water, our collaborators in Japan are way too good at this that we don't have a competitive advantage at all, but our advantage is in doing the gas phase reactions. So basically it's what we can do that's still really relevant to the field, or as relevant as I can be to the field.
Finally, can you cool the cold catalyst system?
Yes, so very good question. So not in the reactor at the moment. I would like to be able to cool the surface of the catalyst, so it's like a cold finger is the coldest part in the reactor, and then water would adsorb onto the surface. So yes, that would be a very good thing to do. I'm not yet sure how to do that in this reactor or any reactor. So I'd like to, but I'm not sure how to do it yet.
Well, I think we really have to thank you very much, Cameron, for taking the time to join us today and then giving us a very good introduction to the problem, the enormous problem that you're trying to solve. That's really fantastic to hear about it. So once again, thank you very much.
Oh, thanks,
Cameron.
Cool.
I'll hand over the baton to Laura.
Yep. And I'll share my screen with the questions. Okay, so hopefully Meredith and Megan can get their screens up and ready. Okay, so I'm absolutely delighted. Oh,
That was my.
can someone put the link in chat just again? Oh, okay. So everyone in chat, there's a link that will take you to this slide so that you can ask a question in the chat and upvote them. And I'm going to facilitate this interview. Is Megan around?
Yeah, I'm here.
Oh, cool. Excellent. So I'm going to facilitate this interview. And I'm just going to start by introducing Megan and Meredith. So I was writing down what I was going to say a bit because I'm a bit nervous about doing this because Meredith and Megan and Michelle Coates, who three amazing women in chemistry and in computational chemistry that I really look up to as a young computational chemist. And yeah, it's a bit humbling to be able to interview you, so thank you very much. Rather than giving you a big career history on them, I wanted to say how I met each of you to the audience. So I met Meredith as an undergraduate researcher at University of Sydney, and we've never actually worked together, interestingly, but we keep trying. But despite that, it has been, I've just had so many great conversations with Meredith about career, about where to go. The encouragement has just been amazing throughout my career. So thank you very much. Megan, I actually didn't overlap with you at ANU. So Megan's at ANU and she came to ANU when I had already finished my PhD at ANU. But I have been absolutely delighted to get to know Megan since I've been back in Australia, and she's awesome. And I think, yeah, I won't say too long. Both Megan and Meredith started their careers as undergraduates in Australia. Actually, I believe pretty much at the same institutions that you're at now. I know Megan was at University of Canberra for a little while and then did a PhD at ANU. And then now is working at ANU, but took some time in Canada, I believe, at the middle of that. Whereas Meredith was at Sydney for a PhD, is now back at Sydney, but took some time in Cambridge at the middle. And yeah. Okay, so maybe I'll just start by asking you guys to briefly introduce yourselves and your area of research to the people that don't know you as well as I do. Meredith, did you want to start?
Okay. Right, so I'm a theoretical chemist and my interest is driven by understanding weird, wacky quantum mechanics because that's the thing that I find really cool. And I come at it much more from a dynamics point of view than, for example, from an electronic structure point of view. So I'm more interested in things like potential energy surfaces and looking at statistics and dynamics of chemical systems and how the surfaces cause the things that we can observe, especially if they're kind of weird and fun. Over the years, I've collaborated with a number of different experimentalists, and it's something that I enjoy immensely, the interplay between theory and experiment. And I think there's a question there somewhere about how do you think of research projects. Can almost answer that one in terms of my career. It's like I follow the things that I find most interesting, and then you sort of have to take a step back and go, okay, so why should I really care about this and fund it? And that's the question you ask.
Yep. And I think well, I'll ask Megan the same question, but that explanation, getting to that, getting to what you do and what you don't do has been a really, it's something I've struggled with and coming to grips with sort of at the moment. So I think a lot of the early career researchers, whether they be honours students, PhD. I know we've got some undergrads, and even the faculty will really appreciate that. Megan, do you want to introduce yourself and your research area?
Hi everyone. Yeah, I'm a computational chemist as opposed to a theoretical chemist. There is a big difference between the two. And yeah, I came to my field through a very kind of meandering career path. Before starting research in my PhD, I actually worked in pathology labs for a few years, and then came back to study physics because I thought it was the best thing in the world to do for some reason, and ended up in doing computational chemistry using molecular dynamics simulations because I'm really interested in how proteins in cells work as molecular machines. So I'm interested in this molecular machinery of the cell and how we can understand living processes using a combination of computational chemistry and understanding the underlying physics of the situation.
That's awesome. And for those of you in the audience who don't know, Megan is actually Katie Wilson's supervisor, who was our first webinar speaker. Okay, so I'm going to defer the what is the best DFT functional until we interview Lars. Sorry, everyone. We're just going to say we've answered that. I did want to link these two things. Oh, there was another one. Oh, if you hadn't become an academic, what would you have done? And I guess related to that, I don't know if you want to answer it separately or afterwards, what career paths have your students taken outside academia? Meredith, did you want to start?
Okay, so I think from about the age of 7, I decided I really wanted to do research science. And I started out because it was more accessible looking at sort of theoretical physics in a sense, and it ended up in theoretical chemistry. So I certainly have had periods where I wasn't sure whether an academic career was going to work out, and did a whole lot of soul searching about what I would do. And if it hadn't worked out, the things that I was most interested in doing were trying to get involved in science policy, and policy planning was something that I'd started investigating. The other option was to go back to university and do a professional degree that had a job at the end of it.
Awesome. Megan?
Yeah, I guess mine's a bit of a no-brainer. As I said, I worked in pathology labs. I also grew up living upstairs from an ambulance centre. My dad was the local ambulance person. And so I was just going to do medicine. It was, you know, but then after working in hospitals for a couple of years, I realised that I'd actually be bored. That after a little while, you'd see the same old things over and over. And I thought really research was more my kind of thing. Every now and then I think it'd be nice just to work from like 9 to 5, earn lots of money, have weekends off.
Well, we can go down to the work-life balance later.
I can come back to what are my students doing outside academia.
Yes.
I have a decent number of them who are working in finance and banking and earning far more money than I do. I even have an ex-postdoc who set up a hedge fund.
Wow.
And I guess in terms of, because the academic career structure is such that not every PhD student can become an academic because that's not going to work. So I guess a lot of the students in the audience might be wanting to know a bit more about what are their options and how does academia prepare them for that? How can they use their research experience to get jobs elsewhere?
Yeah, look, I think that the skills you get from a degree in the physical sciences are just hugely important and are very valued in places like business and finance and modelling. I mean, a lot of the financial institutions recruit people from physical sciences and not from economics or business, for example. Look, I also have students. I have a student who's a senior environmental engineer for BHP. I have another student who went off to join a defence organisation, and if I tell you which one, I might be breaking a secrecy something or other. So they're really good options, and especially the sort of financial modelling option, just because the skills you get And whether it's experimental or sort of theoretical computational physical sciences, those skills are so incredibly useful, and they translate directly into jobs like that. And actually management consulting is another one. I have a number of students who've actually gone off and done teaching and have become fantastic, amazing teachers. And back when we saw real life people would even come back and visit sometimes, which was awesome.
And I guess I'll get to Megan in a moment, but I'd encourage you, we've got a big wealth of knowledge and supervisors that have trained all sorts of different students. If I can ask everyone just in the chat to write down where their students have ended up, where they're thinking of going, and Megan might answer that. And also, yeah, and then we'll ask Megan. I also wanted to know a bit, how did your students get to the jobs? I know in Australia, I mean, look, I wanted to be an academic and that's sort of what I did, but I don't always know, how would I go about getting a job somewhere else? Just apply?
So Megan?
Yep.
Yeah, I think it's really hard if you're just focusing on academic pathways. My last couple of students have all got jobs in consultancy firms, one at PricewaterhouseCoopers and two in Deloitte. And those kind of firms are really trying to recruit people in their STEM think tank areas. And they're also really proactively trying to address gender balance within STEM. So that's a really good thing to see. Yeah, my students just kind of looked for the graduate positions and opening rounds for each one. I had one student who was in the Westpac Future Leaders program in her PhD, and I think that opened a lot of doors for her in terms of helping her think of other career pathways. And then we've been quite fortunate in that she's shared a lot of that knowledge to the next lot of students coming through the group. Yeah.
And I guess one thing I did want to say is part of the benefit of having this community is that you do have some other people that you can go and meet with and talk to, and awesome.
Yeah.
I might just go to, what is the most useful skill you can learn as a student, maybe that will set you up for academia or non-academia, and then we might go to some more academic things. I did want to get, okay, we'll do that. Best skill you can learn as a student.
So I think is to keep learning. So that's the biggest message is just act like a sponge and soak up all the knowledge you possibly can, because who knows when it will be useful, and you have such a fantastic opportunity to do that. And I was talking to Laura earlier in the week. If I had to nominate the single most useful skill right this second at the moment, I go Python.
Yep.
I like that one. Mine, I've looked at it from a different perspective. Python is really, really useful. I'm a terrible coder and I really wish I had better coding skills. But I think project management and communication skills, because you always need to communicate your science, but you also need to be able to manage your time and projects and communicate to people outside your field. And I think that this will they're kind of skills that will set you up everywhere.
And actually, I guess that links very naturally to, why don't we talk about what is your advice for ECRs wanting to get their first DP solo grant? So how do you, and I guess how do you decide what research directions to pursue? And then how do you start to get grants for that?
Okay, so my advice on this one is try and take the step back and look at the big picture. So to get the grant, you actually need a combination of lots of things. So you need good ideas. You need to be able to flesh those ideas out into a sensible and coherent plan. But the very most important thing is you need to be able to sell all of that in terms of your experience and expertise. And so I do find when I'm helping people and editing grants is that lots of people just don't quite take enough of a step backwards to see the really big picture, and to put the work into the overall context. if that makes sense.
Yep, definitely. Megan?
Yeah, I agree with that. The other thing I would tell people is don't expect to crack it the first year. Don't, you know, you may have had the most stellar career path ever so far, but, you know, I was devastated when I didn't get my first grant. It was one of the most crushing moments of my life because I thought it was a wonderful grant. I was so close to the project. But, you know, I think, yeah, being able to kind of keep some perspective, getting a lot of advice from a mentor in this, or going in with someone who's had experience in the system before, then managing your expectations, because a lot of people just leave science because they're used to being very good at what they do, they're used to being very creative, and they're usually very driven, successful people. And overcoming that hurdle to get a grant and get rejected like that is sometimes quite a tough thing to do.
Yeah, look, I would agree with that, the managing expectations. And it's interesting, so I have a child who's an elite athlete. They're great. Like, they have psychologists, they have all of this support around them to help them manage the expectations when things don't quite work out. And in a sense, the whole process of applying for grants and then having to deal with the reviewers and the rebuttals, to me, it's actually exactly the same. The only difference is we don't offer the same level of support that an athlete would be given. So if you sort of think about it in that sense, that it's a really, really difficult thing. And I don't know if that helps anybody, but all of us have had horrendous reviews and have had to somehow bring ourselves back from the brink after reading a grant review. And that's a universal experience.
And I have to say, this was my third time round ARC this year. And I think I can say I was most proud of the fact that it didn't derail an entire 2-week period when I got my grant reviews back. I managed to get something done in that period that was not just stressing about it. I think that's quite, I'm glad it's not just me.
No, I think it always makes you think about imposter syndrome. You know, am I here because I'm actually kind of good at what I do? Or have I just fooled everyone up until now, and then suddenly this reviewer has seen me for what I am and realizes that I'm actually just a big fraud? You know, it's, managing those expectations and being able to put things in perspective and realizing that some people just write grants when they're in a very bad mood. Write reviews.
Yeah, write reviews.
Write reviews, yeah. No, and I guess everyone that's doing grants, remember that if you get a really bad comment, you can complain now. 3 days. So why don't we go here? And I guess it's related to when you're deciding which research directions to pursue, when do you decide it's not working? When do you stop, and how do you stop the project in a way that, and I guess it's similar when you're writing a grant, when do you decide, well, hang on, that grant's not going to be funded, move on?
Look, it comes down to research design. So I was looking at this question, scratching my head going, okay, how do I answer that? And I think really good research design means you ask a question for which the answer is itself really important. Like, it doesn't matter what the answer is, but answering the question either one way or another is what's important. So it's not that it doesn't work. It might not give you what you expected. And I've had plenty of opportunities to deal with things coming out differently to what my initial thoughts were. But if you design a research project so that you follow those routes, it's not that it doesn't work. It's just taking you in a different direction. That was the best way I could think of to answer that question.
I think that's a beautiful answer. Megan?
Yeah, I agree.
Yep.
Yeah.
Okay. Yep, no, that's good.
I can share something here. once that one of my mentors actually told me. And when I was saying what I'm doing just seems to be so incredibly simple and obvious. And he took me aside and said, but the best science is the bit that's simple and obvious. So don't be afraid to do something simple either. And a part of that is anybody can ask a question that has a really complicated, difficult to understand answer. The art is to ask the question that has a simple answer.
And then I guess the key is when you get that simple answer, you need to figure out, does everyone else already know it?
Yeah, I think that was why I was feeling guilty. And he just went, no. When you've got something like that, take it, run with it.
Yep. Excellent.
Meredith, sorry, may I interrupt for a second? Meredith, you touch on a topic there on mentorship.
Yeah.
So can you maybe, Megan and Meredith, would you be able to share with us the sort of mentorship you received when you were starting your career, and how that can be very important for our younger generations?
Megan, maybe do you want to go first?
Okay. I had really good mentorship when I was at University of Queensland throughout my postdoc. My mentor there was Alan Mark, and I don't know, I'm sure most of you have met Alan. He's a challenging person, and no, I've got enormous, I say that I've got enormous respect for Alan, and I really like him as a person. What I mean by he's challenging is he always asks you the hard questions, and he does things that, he gives you the hard feedback that no one else would ever give you. Like, you've got to come up with a research vision. Having a project isn't enough. What's your vision? And I remember him drilling me for months when I was preparing to go for academic positions, saying, well, that's not really a vision yet. What's your vision? And things like that. And I found that even though at the time it was, some of Alan's comments and criticism were really difficult to get my head around, they've been the most beneficial for me in the long term. As well as that, I had a really good network of peer mentors through my student years and also my postdoc in Canada. And that was really beneficial because you could see what other people wanted to do. And you had people to bounce ideas off, and in a really kind of non-judgmental way where, hey, this is a crazy, stupid idea, but I'm going to go for it anyway, and it might get me somewhere. So both of those things I think have been really, really beneficial.
Yeah, so for me, I guess I didn't even think about mentorship or being mentored until I went to, sorry, that was my computer reminding me of things, until I went to Cambridge. So I was in just the wonderful position to have David Buckingham, who's actually an expat Australian, who was Professor of Theoretical Chemistry at Cambridge as a mentor, and David Clary, who is also just absolutely phenomenal. And just the strategic advice and the things like the big picture, making the most of something when you find something that's relatively simple, just make the most of that. A whole lot of career advice, things like how to write, even how to write a paper. David Buckingham gave me some wonderful advice that I've tried to pass on to all my students in terms of how do you write that paper, how do you get it through, and get it into really good journals. And David Clary has been the most incredible mentor and just been so supportive all throughout my career. So I've been very lucky in that sense.
So, and how did you, one of the things I struggle with is how do you ask for time, or how often should you meet with the mentors, and what sort of questions and what sort of feedback should you be seeking, and I guess when? As much as you can, as often
Yeah.
as you can, or?
Look, for me, what I did do was I'd say, oh, I'm about to apply for this job. Would you be a referee for me first up, and then could you give me some feedback on my job application, for example? That came up quite a lot. Went through that process a lot of times, and similarly for things like promotion applications, and talking through ideas at conferences. That was a really good place. Sort of subsequently, I saw David a number of times after I came back from England, and I guess it wasn't really formal in that sense, but then that was sufficiently long ago that mentoring itself wasn't really formal either.
And I guess the other part of, and some of these other questions are sort of saying, I wanted to touch on the fact, how do you balance all the aspects of your life, and did you have any comments that you feel, or not balanced? I guess, I mean, there's a question here that some people, when do you decide to have kids? How do you, there was a question also up here, what was your favorite extracurricular activity in your time off? Do you have any thoughts about how you can start to stay somewhat sane?
The two things are linked together. How do you balance things? I don't know if I do balance things. I feel like I'm clinging on by my fingernails most of the time. And in terms of the extracurricular activities, I like doing things and making things. So I'll go and dig up my garden, or if I've had a really bad week, I'll just pull out weeds, because I can then point to the garden bed and go, see, look, I did that, I achieved something. And I think things like that are actually really important, that you have things that are separate to your existence as a researcher, because every so often just research doesn't go anywhere for a while, and you have to somehow cope with that. So being able to look at other aspects of your life, I think is really important to try and maintain a balance and a sanity.
Megan?
I agree. I've also done a lot of therapeutic weeding in the past. Because,
Yep.
and some therapeutic hedge trimming and that.
Oh yeah, pruning.
Yeah, pruning is good. Apart
Are
from
you
that,
saying a garden is an essential part? I don't know. I live in the city. I wasn't going to garden, but
look, if you've got your own apartment and you can renovate, and you can, bashing down a wall, there's nothing quite like it when you've had a really bad week at work.
You could knit a scarf as well, because you can actually see it growing in front of you.
for me, it's definitely craft. So my PhD, I made scarves coming out my ears. Now it's soap making. I've got a box. Does anyone want any soap? Like, seriously? It's about this big. Yeah. I guess I didn't want to keep people I wanted to give a little bit of time for our breakout sessions. Is there something you'd like to sort of share with the community, some advice, or last words? That sounds really bad. Final comments or thoughts?
All right, so this is another piece of advice that this one's from David Clary, and I had my first child when I was a postdoc in Cambridge, and he was born in England. And I remember David saying I was almost apologetic, saying, I'm going to have a baby, the baby's due in whatever day. And he was just so over the moon, and it was just wonderful. And he said, there's no right time to have children, which means whenever you do have children, therefore it is the right time. And that if you want to have kids, don't leave it too late was something that I will never forget him saying, because I do know people who have left it later. And in many ways, this is a very flexible kind of career, and it does give you those opportunities to have a family and to have family commitments and balance them with an academic career if that's what you want to do. So you can, and it's getting easier and easier, which is absolutely fantastic.
And I have to, well, I'm hoping COVID's
Oh, yes.
showing people that you can effectively work from home and be flexible. And I mean, even when we have in-person meetings, I'm hoping that we have the option almost in most meetings to video in. Silver linings.
Yeah. And I just love, his phrase was that it is the right time, was what was so really nice, because it was so affirming.
That's really fantastic. I have to admit, when I told my postdoc supervisor in Canada that I was pregnant, I kind of went in there because my experience in Australia was that, you know, you're dooming your scientific career. And he kind of took it in good stride. And then I heard later from his wife, actually, that he was so shocked by my kind of coming in there and, oh, I'm really sorry to tell you, but I'm pregnant. That he didn't know whether to congratulate me or not, because he wasn't sure if I actually yeah, and I did. So it was a wanted pregnancy, and so that was really great. It was a different cultural perspective that I think that Australians have only recently embraced the whole idea that you can have a research career and still be a parent of a young child. My big piece of advice would be make sure your contract has more than 12 months on it after you have your child, if that's possible, so that you do get the maternity or parental leave built into it.
Yeah.
Yeah.
And I guess the other bit of advice there is that there's enough senior people that if you're not sure what's going on, most universities have EDI committees at the moment. We've got the RACI EDI committee that can come and help fight for you if you're in a situation where you don't get those sort of positive responses that Meredith and me had. Okay, so we're going to break into some breakout rooms. I'm not sure how many we're going to do, but just so that everyone else in this chat can have a bit of a chance to talk to.